Today I am going to teach you how to make neural nets from scratch. This is for complete beginners. If you want to download the source, check the link in description. Along with source code, get the complete explanation. Now let's start with the video. Let's say you want to predict some output value y, given some input value x. For example, maybe you want to predict your score on a test based on how many hours you sleep and how many hours you study the night before. To use a machine learning approach, we first need some data. Let's say for the last 3 tests, you recorded your number of hours of studying, your number of hours sleeping, and your score on the test. We'll use the programming language Python to store our data in 2-dimensional NumPy arrays. Populating the interactive namespace from NumPy and Matplotlib. This code is a magic command used in Jupyter notebooks or IPython environments to enable the inline plotting of graphs and figures generated by Matplotlib, a popular plotting library for Python. The %pylab command is a shorthand for importing several commonly used scientific Python libraries, including NumPy, Matplotlib, and IPython, and it allows for the interactive exploration of data using graphs and figures directly within the notebook environment. The inline argument specifies that the graphs and figures should be displayed within the notebook itself, rather than in a separate window or external application. This is particularly useful when working in a notebook environment, as it allows for a seamless integration of data exploration, analysis, and visualization. X equals hours sleeping, hours studying, y equals score on test. In this code snippet, we are initializing 2 NumPy arrays x and y that represent our input and output data for a neural network. The x array contains 3 input samples, each with 2 features: the number of hours the student slept the night before the test, and the number of hours the student studied for the test. These input features are represented as a 2D NumPy array with shape 3, 2, where each row represents an input sample and each column represents a feature. The y array contains the corresponding target values for each input sample, which are the scores the students received on the test. These target values are represented as a 2D NumPy array with shape 3, 1, where each row represents a target value for the corresponding input sample. The type equals float argument specifies that the data in both arrays should be stored as floating point numbers, which is typically used for numerical computations in neural networks. The code x simply outputs the NumPy array x, which was defined earlier in the code snippet. The code y simply outputs the NumPy array x, which was defined earlier in the code snippet. Now that we have some data, we're going to use it to train a model to predict how you will do on your next test, based on how many hours you sleep and how many hours you study. This is called a supervised regression problem. It's supervised because our examples have inputs and outputs. It's a regression problem because we're predicting your test score, which is a continuous output. If we were predicting your letter grade, this would be called a classification problem, and not a regression problem. There are an overwhelming number of models within machine learning. Here we're going to use a particularly interesting one called an artificial neural network. These guys are loosely based on how the neurons in your brain work, and have been particularly successful recently at solving really big, really hard problems. Before we throw our data into the model, we need to account for the differences in the units of our data. Both of our inputs are in hours, but our output is a test score, scaled between 0 and 100. Neural networks are smart, but not smart enough to guess the units of our data. It's kind of like asking our model to compare apples to oranges, where most learning models really only want to compare apples to apples. The solution is to scale our data. This way our model only sees standardized units. Here, we're going to take advantage of the fact that all of our data is positive, and simply divide by the maximum value for each variable, effectively scaling the result between 0 and 1. Max test score is 100. In this code snippet, we are scaling the input features in the X array and normalizing the target values in the Y array. The first line of code scales the input features in X by dividing each element of X by the maximum value along each column. The np.mx, x, axis equals 0, function computes the maximum value along each column, i.e., the maximum value of hours slept and hours studied, respectively, and the slash operator applies element-wise division to each element in X. This scales each input feature to be between 0 and 1, which is a common preprocessing step for neural networks. The second line of code normalizes the target values in Y by dividing each element of Y by 100, since the maximum test score is 100. This scales each target value to be between 0 and 1, which is also a common preprocessing step for neural networks. Note that scaling and normalizing the input and output data can help improve the performance and convergence of neural networks by making the optimization process smoother and more efficient. Now we can build our neural net. We know our network must have 2 inputs and 1 output, because these are the dimensions of our data. We'll call our output y hat, because it's an estimate of y, but not the same as y. Any layer between our input and output layer is called a hidden layer. Recently, researchers have built networks with many hidden layers. These are known as deep belief networks, giving rise to the term deep learning. Here, we're going to use one hidden layer with 3 hidden units, but if we wanted to build a deep neural network, we would just stack a bunch of layers together. This code imports the image class from the ipython.display module, and then creates an instance of the image class from a file named images/simplenetwork.png. The purpose of this code is to display an image of a simple neural network architecture in a Jupyter notebook, or IPython shell. The image class allows you to display images directly in the notebook environment, and the file name argument specifies the path to the image file to be displayed. Assuming that the image file images/simplenetwork.png exists in the current working directory, running this code will display the image of the simple neural network in the notebook, or shell. In neural net visuals, circles represent neurons and lines represent synapses. Synapses have a really simple job. They take a value from their input, multiply it by a specific weight, and output the result. Neurons are a little more complicated. Their job is to add together the outputs of all their synapses, and apply an activation function. Certain activation functions allow neural nets to model complex nonlinear patterns that simpler models may miss. For our neural net, we'll use sigmoid activation functions. Next, we'll build out our neural net in Python. Part 2, Forward Propagation. This time, we'll implement it in the programming language Python. We'll build our network as a Python class, and our init method will take care of instantiating important constants and variables. We'll make these values accessible to the whole class by placing a self dot in front of each variable name. Our network has 2 inputs, 3 hidden units, and 1 output. These are examples of hyperparameters. Hyperparameters are constants that establish the structure and behavior of a neural network, but are not updated as we train the network. Our learning algorithm is not capable of, for example, deciding that it needs another hidden unit. This is something that we must decide on before training. What a neural network does learn our parameters, specifically the weights on the synapses. We'll take care of moving data through our network in a method called forward. Rather than pass inputs through the network one at a time, we're going to use matrices to pass through multiple inputs at once. Doing this allows for big computational speedups, especially when using tools like MATLAB or NumPy. Our input data matrix, X, is of dimension 3 by 2, because we have 3 two-dimensional examples. Our corresponding output data, Y, is of dimension 3 by 1. This code prints the shapes of the X and Y NumPy arrays to the console. The shape attribute of a NumPy array returns a tuple of integers that represent the dimensions of the array. In this case, x.shape returns 3, 2, indicating that x has 3 rows, corresponding to 3 input samples, and 2 columns, corresponding to 2 input features. Similarly, y.shape returns 3, 1, indicating that y has 3 rows, corresponding to 3 target values, and 1 column, corresponding to 1 output. Printing the shapes of the x and y arrays is a useful debugging step to ensure that the data is loaded correctly and has the expected dimensions before training a neural network. Define hyperparameters. Propagate inputs to network. This code defines a Python class called neural_network, which represents a neural network object. The class has an __init___ method that initializes the hyperparameters of the network, and a forward method that performs the forward propagation of inputs through the network. The __init___ method defines the hyperparameters of the network, which are the input layer size, output layer size, output layer size, and hidden layer size. These hyperparameters are typically set by the user and determine the architecture and size of the neural network. The forward method takes an input x as an argument and performs the forward propagation of inputs through the network. However, the forward method is currently empty, pass, so it does not perform any actual computations yet. The purpose of the forward method is to compute the output of the neural network given an input, which will involve matrix multiplication, activation functions, and other operations depending on the specific architecture of the network. Note that this code defines only the structure of the neural network object and does not include any training or learning algorithms yet. Each input value, or element in matrix X, needs to be multiplied by a corresponding weight and then added together with all the other results for each neuron. This is a complex operation, but if we take the 3 outputs we're looking for as a single row of a matrix and place all our individual weights into a matrix of weights, we can create the exact behavior we need by multiplying our input data matrix by our weight matrix. Using matrix multiplication allows us to pass multiple inputs through at once by simply adding rows to the matrix X. From here on out, we'll refer to these matrices as X, W1, and Z2, where Z2 the activity of our second layer. Notice that each entry in Z is the sum of weighted inputs to each hidden neuron. Z is of size 3 by 3, 1 row for each example, and 1 column for each hidden unit. We now have our first official formula, Z2 equals XW1. Matrix notation is really nice here, because it allows us to express the complex underlying process in a single line. Now that we have the activities for our second layer, Z2, we need to apply the activation function. We'll independently apply the function to each entry in matrix Z using a Python method for this called sigmoid, because we're using a sigmoid as our activation function. Using numpy is really nice here, because we can pass in a scalar, vector, or matrix. Numpy will apply the activation function element-wise and return a result of the same dimension as it was given. Apply sigmoid activation function to scalar, vector, or matrix. This code defines a Python function called sigmoid, which applies the sigmoid activation function to a scalar, vector, or matrix input Z. The sigmoid function is a common activation function used in neural networks that maps any input value to a value between 0 and 1. Here exp is the exponential function and z is the input. The sigmoid function defined in this code uses the NumPy library to apply the sigmoid function element-wise to the input z. Specifically, the np.exp function computes the exponential of each element of z, and the slash and plus operators apply element-wise division and addition to compute the sigmoid function. This function is useful for computing the activation of neurons in the neural network during the forward propagation step, as it allows the network to model nonlinear relationships between inputs and outputs. This code generates a plot of the sigmoid function over a range of input values using the plot function from the matplotlib library. The test input numpy array is created using the np.arrange function, which creates an array of evenly spaced values between -6 and 6, with a step size of 0.01. This array is used to define the x-axis values of the plot. The plot function takes two arguments, the x-axis values, test input, and the corresponding y-axis values, which are the output of the sigmoid function applied to the test input array. The line width argument sets the width of the line in the plot. The grid function adds a grid to the plot for improved readability. Overall, this code generates a plot of the sigmoid function over a range of input values, which is a common visualization used to understand the behavior of the sigmoid function and its role in neural networks. The plot should show an S-shaped curve that approaches 0 for large negative inputs and 1 for large positive inputs, with a midpoint of 0.5. The code sigmoid 1 computes the output of the sigmoid function when the input z is equal to 1. This code applies the sigmoid function element-wise to a 1D numpy array with 3 elements, -1, 0, 1, using the sigmoid function defined earlier. The sigmoid function computes the sigmoid of each element of the input array, resulting in a new numpy array with the same shape as the input array. In this case, the input array np.array-1, 0, 1 is passed to the sigmoid function, which applies the sigmoid function element-wise to each element of the array. This output array represents the sigmoid of each element in the input array, where the first element, -1, is mapped to a value close to 0, the second element, 0, is mapped to 0.5, and the third element, 1, is mapped to a value close to 1. Overall, this code applies the sigmoid function to a numpy array, which is a common operation in neural networks for computing the activation of neurons during the forward propagation step. This code applies the sigmoid function element-wise to a 3x3 numpy array of random values generated from a normal distribution with mean 0 and standard deviation 1 using the np.random.ran function. The np.random.ran function creates an array of random values from a standard normal distribution, i.e., with mean 0 and standard deviation 1. The 3 argument specifies the shape of the array to be created. The resulting 3x3 numpy array of random values is then passed as an argument to the sigmoid function defined earlier, which applies the sigmoid function element-wise to each element of the array, resulting in a new 3x3 numpy array with the same shape. The output of the sigmoid, np.random.ran 3 code is a 3x3 numpy array of sigmoid values, where each element is the sigmoid of the corresponding element in the input array. Since the input values are random, the output values will also be random, but they will be between 0 and 1 due to the sigmoid function. We now have our second formula for forward propagation. Using f to denote our activation function, we can write that a 2, our second layer activity, is equal to f of z2. A 2 will be a matrix of the same size as z2, 3x3. To finish forward propagation, we need to propagate a 2 all the way to the output, yacht. We've already done the heavy lifting in the previous layer, so all we have to do now is multiply a 2 by our second layer weights w2 and apply one more activation function. w2 will be of size 3x1, one weight for each synapse. Multiplying a2, a 3x3, by w2, a 3x1 results in a 3x1 matrix z3, the activity, or our third layer. z3 has 3 activity values, one for each example. Last but not least, we'll apply our activation function to z3 yielding our official estimate of your test score, y hat. We need to implement our forward propagation formulas in Python. First, we'll initialize our weight matrices in our init method. For starting values, we'll use random numbers. We'll implement forward propagation in our forward method, using numpy's built-in dot method for matrix multiplication and our own sigmoid method. Define hyperparameters. weights, parameters. Propagate input still network. Apply sigmoid activation function to scalar, vector, or matrix. This code is an updated version of the neural_network class that we saw earlier. This version includes additional code that initializes the weights, parameters, of the neural network and performs the forward propagation step. In the __init___ method, two weight matrices W1 and W2 are initialized using the np.random.ran function. W1 is a matrix of weights connecting the input layer to the hidden layer, with shape, input layer size, hidden layer size. W2 is a matrix of weights connecting the hidden layer to the output layer, with shape, hidden layer size, output layer size. These weight matrices are randomly initialized using values from a normal distribution with mean 0 and standard deviation 1, which is a common initialization method for neural networks. In the forward method, the forward propagation of inputs through the network is performed using the weight matrices and the sigmoid activation function. Specifically, the dot product of the input x and the weight matrix W1 is computed to obtain the weighted sum of the inputs for the hidden layer, self.z2. The sigmoid of self.z2 is computed to obtain the activation of the hidden layer, self.a2. The dot product of self.a2 and W2 is computed to obtain the weighted sum of the activations for the output layer, self.c3. Finally, the sigmoid of self.c3 is computed to obtain the predicted output, y hat. The sigmoid method is a helper method that applies the sigmoid activation function to a scalar, vector, or matrix input z, as we saw earlier. Overall, this code defines a basic neural network object with a forward propagation method that takes an input and returns a predicted output. The weights of the network are randomly initialized using a normal distribution, but they will be updated during the training process using backpropagation. And there you have it, a Python class capable of estimating your test score given how many hours you sleep and how many hours you study. We can pass in our input data and get real outputs. Now, you may be noticing that our estimates are quite terrible. That's because we have not yet trained our network. That's what we'll work on next time. Part 3. Great. Gradient descent. Last time we built a neural network in Python that made really bad predictions of your score on a test based on how many hours you slept and how many hours you studied the night before. This time we'll focus on the theory of making those predictions better. We can initialize the network we built last time and pass in our normalized data, x, using our forward method, and have a look at our estimate of y hat. This code creates an instance of the neural_network class and assigns it to a variable called nn. The neural_network syntax calls the constructor method __init__ of the neural_network class, which initializes the hyperparameters and weights of the network. The resulting instance of the neural_network class is stored in the variable nn. class to train and evaluate the neural network on a specific task, such as by creating an instance of the neural_network class. We can now use the methods and attributes of the class to train and evaluate the neural network on a specific task, such as the regression problem we saw earlier. This code performs a forward pass through the neural network NN to obtain the predicted output, y hat, given an input x. The forward method of the NN object takes the input x as an argument and performs the forward propagation of inputs through the network, as we saw earlier. Specifically, it computes the dot product of the input x and the weight matrix W1 to obtain the weighted sum of the inputs for the hidden layer, self.c2. It then applies the sigmoid function to self.c2 to obtain the activation of the hidden layer, self.a2. It computes the dot product of self.a2 and w2 to obtain the weighted sum of the activations for the output layer, self.c3. Finally, it applies the sigmoid function to self.c3 to obtain the predicted output, y hat. By calling the forward method of the NN object with the input x as an argument, we obtain the predicted output of the network for the given input. This is the first step in training and evaluating the neural network on a specific task, such as the regression problem we saw earlier. Y hat is a NumPy array containing the predicted output of the neural network for the input x. The NN.forward x code performs a forward pass through the neural network NN with the input x to obtain the predicted output, as we saw earlier. The output is stored in the y hat variable. Since y hat is a NumPy array, we can inspect its values and shape by printing it to the console using the print function, or by calling its shape attribute. Compare estimate, y hat, to actually score. This code creates a bar plot that compares the actual target values y with the predicted values y had obtained from the neural network. The bar function from the matplotlib library is used to create the bar plot. The first argument to bar is a list of x-axis values where each bar will be plotted. In this case, the list is 0, 1, 2, indicating that there are 3 bars to be plotted. The second argument to bar is a list of y-axis values corresponding to the heights of the bars. The y.flatten syntax flattens the y_NumPy array into a 1D array before passing it to bar, so that it can be plotted as a sequence of bars. 2 sets of bars are plotted side by side. The first set of bars corresponds to the actual target values y, plotted in blue using the alpha argument to set the opacity to 0.8. The second set of bars corresponds to the predicted values y hat, plotted in red using the color argument to set the color to red and the alpha argument to set the opacity to 0.8. The second set of bars is shifted by 0.35 units along the x-axis to make it appear next to the first set of bars. The legend function adds a legend to the plot, indicating which bars correspond to y and y hat. The grid function adds a grid to the plot for improved readability. Overall, this code creates a bar plot that visually compares the actual target values with the predicted values obtained from the neural network. Right now our predictions are pretty inaccurate. To improve our model, we first need to quantify exactly how wrong our predictions are. We'll do this with a cost function. A cost function allows us to express exactly how wrong or costly our models is, given our examples. One way to compute an overall cost is to take each error value, square it, and add these values together. Multiplying by 1/2 will make things simpler down the road. Now that we have a cost, our job is to minimize it. When someone says they're training a network, what they really mean is that they're minimizing a cost function. Our cost is a function of 2 things, our examples, and the weights on our synapses. We don't have much control of our data, so we'll minimize our costs by changing the weights. Conceptually, this is pretty simple concept. We have a collection of 9 individual weights, and we're saying that there is some combination of w's that will make our cost, j, as small as possible. When I first saw this problem in machine learning, I thought, I'll just try all the weights until I find the best one. After all, I have a computer. Enter the curse of dimensionality. Here's the problem. Let's pretend for a second that we only have one weight, instead of 9. To find the ideal value of our weight that will minimize our cost, we need to try a bunch of values for w. Let's say we test 1000 values. That doesn't seem so bad. After all, my computer is pretty fast. This code defines a grid search over a range of weights to try for the neural network. Specifically, it loops over 1000 weight values, weights to try, ranging from -5 to 5, and for each weight value, it sets the value of the weight at the 0, 0 position of the weight matrix W1 in the NN object. It then performs a forward pass through the network with the input x to obtain the predicted output y hat, and computes the mean squared error cost between the predicted output and the actual target output y. The cost is stored in the costs numpy array. The purpose of this code is to evaluate the performance of the neural network with different weight values and to identify the weights that lead to the lowest cost. The costs array will contain the costs for each weight value, and we can use this information to identify the weight that leads to the lowest cost and update the weights of the neural network accordingly. The time.process_time function is used to measure the execution time of the code. Specifically, it records the start time before the loop and the end time after the loop, and computes the difference to obtain the total execution time. This information can be useful for profiling and optimizing the performance of the code. This code computes the difference between the end time and start time variables, which were set using the time.process_time function before and after the loop, respectively. The result is stored in the time-elapsed variable. The time-elapsed variable contains the total execution time of the loop, measured in seconds. This information can be useful for profiling and optimizing the performance of the code, and for comparing the execution time of different versions of the code or different algorithms. It takes about 0.07 seconds to check 1000 different weight values for our neural network. Since we've computed the cost for a wide range of values of W, we can just pick the one with the smallest cost, let that be our weight, and we've trained our network. This code creates a plot of the costs computed in the previous loop against the weight values that were tried. The plot function from the matplotlib library is used to create the plot. The first argument to plot is the x-axis values, which are the weight values that were tried, weights to try. The second argument to plot is the y-axis values, which are the costs computed for each weight value in the loop, costs. The label function adds a label to the y-axis of the plot, which is cost, in this case. This label function adds a label to the x-axis of the plot, which is weight, in this case. The grid function adds a grid to the plot for improved readability. Overall, this code creates a plot that shows the relationship between the weights tried and the corresponding costs computed for each weight value. The purpose of this plot is to help identify the weight values that lead to the lowest cost and to update the weights of the neural network accordingly. So you may be thinking that 0.04 seconds to train a network is not so bad, and we haven't even optimized anything yet. Plus, there are other, way faster languages than Python are there. Before we optimize through, let's consider the full complexity of the problem. Remember, the 0.04 seconds required is only for one weight, and we have 9 total. Let's next consider 2 weights for a moment. To maintain the same precision, we now need to check 1000 times 1000, or 1 million values. This is a lot of work, even for a fast computer. This code performs a more exhaustive grid search over a larger range of weight values to try for the neural network. Specifically, it loops over 1000 weight values, weights to try, ranging from -5 to 5 for 2 different weights, W1, 0, 0, and W1, 0, 1, resulting in a total of 1000 by 1000 weight combinations. For each weight combination, it sets the values of the weights in the weight matrix W1 in the NN object. It then performs a forward pass through the network with the input x to obtain the predicted output y hat, and computes the mean squared error cost between the predicted output and the actual target output y. The cost is stored in the costs numpy array. The purpose of this code is to perform a more comprehensive evaluation of the performance of the neural network with different weight values and to identify the weights that lead to the lowest cost. The cost array will contain the cost for each weight combination, and we can use this information to identify the weight combination that leads to the lowest cost and update the weights of the neural network accordingly. The time.process_time function is used to measure the execution time of the code. Specifically, it records the start time before the loop and the end time after the loop, and computes the difference to obtain the total execution time. This information can be useful for profiling and optimizing the performance of the code. This code computes the difference between the end time and start time variables, which were set using the time.process_time function before and after the loop, respectively. The result is stored in the time-elapsed variable. The time-elapsed variable contains the total execution time of the loop, measured in seconds. This information can be useful for profiling and optimizing the performance of the code, and for comparing the execution time of different versions of the code or different algorithms. Note that this loop over 1000 by 1000 weight combinations is much more computationally expensive than the previous loop over 1000 weight values, and the execution time will be significantly longer. After our 1 million evaluations, we found our solution, but it took an agonizing 62 seconds. The real curse of dimensionality kicks in as we continue to add dimensions. Searching through 3 weights would take a billion evaluations, or 11 hours. Searching through all 9 weights we need for our simple network would take 1,268,391,679,350,583.5 years. Over a quadrillion years. So for that reason, the just try everything, or brute force optimization method is clearly not going to work. Let's return to the one-dimensional case and see if we can be more clever. Let's evaluate our cost function for a specific value of w. If w is 1.1 for example, we can run our cost function and see that j is 2.8. Now we haven't learned much yet, but let's try to add a little information to what we already know. What if we could figure out which way was downhill? If we could, we would know whether to make w smaller or larger to decrease the cost. We could test the cost function immediately to the left and right of our test point and see which is smaller. This is called numerical estimation and is sometimes a good approach, but for us, there's a faster way. Let's look at our equations so far. We have 5 equations, but we can really think of them as one big equation. And since we have one big equation that uniquely determines our cost, j, from x, y, w1, and w2, we can use our good friend calculus to find what we're looking for. We want to know which way is downhill. That is, what is the rate of change of j with respect to w, also known as the derivative. And in this case, since we're just considering one weight at a time, the partial derivative, we can derive an expression for dj dw that will give us the rate of change of j with respect to w for any value of w. If djw is positive, then the cost function is going uphill. If djw is negative, the cost function is going downhill. Now we can really speed things up. Since we know in which direction the cost decreases, we can save all that time we would have spent searching in the wrong direction. We can save even more computational time by iteratively taking steps downhill and stopping when the cost stops getting smaller. This method is known as gradient descent, and although it may not seem so impressive in one dimension, it is capable of incredible speedups in higher dimensions. In fact, in our final video, we'll show that what would have taken 10 to the power of 27 function evaluations with our brute force method will take less than 100 evaluations with gradient descent. Gradient descent allows us to find needles in very, very, very large haystacks. Now, before we celebrate too much here, there is a restriction. What if our cost function doesn't always go in the same direction? What if it goes up then back down? The mathematical name for this is nonconvex, and it could really throw off our gradient descent algorithm by getting it stuck in a local minima instead of our ideal global minima. One of the reasons we chose our cost function to be the sum of squared errors was to exploit the convex nature of quadratic equations. We know that the graph of y equals x squared is a nice convex parabola, and it turns out that higher dimensional versions are too. Another piece of the puzzle here is that depending on how we use our data, it might not matter if our cost function is convex or not. If we use our examples one at a time instead of all at once, sometimes it won't matter if our cost function is convex, we will still find a good solution. This is called stochastic gradient descent. The details of gradient descent are a deep topic for another day. For now, we're going to do our gradient descent, batch style, where we use all our example at once, and the way we've set up our cost function will keep things nice and convex. Next time we'll compute and code up our gradients. Last time, we decided to use gradient descent to train our neural network, so it could make better predictions of your score on a test based on how many hours you slept and how many hours you studied the night before. To perform gradient descent, we need an equation and some code for our gradient, dj/dw. Our weights, w, are spread across two matrices, w1 and w2. We'll separate our dj/dw computation in the same way, by computing dj/dw1 and dj/dw2 independently. We should have just as many gradient values as weight values, so when we're done, our matrices dj/dw1 and dj/dw2 will be the same size as w1 and w2. Let's work on dj/dw2 first. The sum in our cost function adds the error from each example to create our overall cost. We'll take advantage of the sum rule in differentiation, which says that the derivative of the sums equals the sum of the derivatives. We can move our sigma outside and just worry about the derivative of the inside expression first. To keep things simple, we'll temporarily forget about our summation. Once we've computed dj/dw for a single example, we'll add all our individual derivative terms together. We can now evaluate our derivative. The power rule tells us to bring down our exponent, 2, and multiply. To finish our derivative, we'll need to apply the chain rule. The chain rule tells us how to take the derivative of a function inside of a function, and generally says we take the derivative of the outside function and then multiply it by the derivative of the inside function. One way to express the chain rule is as the product of derivatives. This will come in very handy as we progress through backpropagation. In fact, a better name for backpropagation might be, don't stop doing the chain rule. Ever. We've taken the derivative of the outside of our cost function, now we need to multiply it by the derivative of the inside. Y is just our test scores, which won't change, so the derivative of y, a constant, with respect to w2 is 0. Y hat, on the other hand, does change with respect to W2, so we'll apply the chain rule and multiply our results by minus d/dw2. We now need to think about the derivative of y hat with respect to W2. Equation 4 tells us that y hat is our activation function of z3, so it will be helpful to apply the chain rule again to break dy hat/dw2 into dy hat/dz3 times dz3/dw2. To find the rate of change of y hat with respect to z3, we need to differentiate our sigmoid activation function with respect to z. Now is a good time to add a new Python method for the derivative of our sigmoid function, sigmoid prime. Our derivative should be the largest where our sigmoid function is the steepest, at the value z equals 0. Apply sigmoid activation function to scalar, vector, or matrix. This code defines the sigmoid activation function, which is commonly used in neural networks to introduce nonlinearity in the output of a neuron. The sigmoid function takes a scalar, vector, or matrix Z as input and applies the sigmoid function to each element of the input. The sigmoid function is defined as 1/1 plus exp z, where exp is the exponential function. When the input z is a scalar, the sigmoid function returns a scalar value between 0 and 1, representing the activation level of a neuron. When the input z is a vector or matrix, the sigmoid function applies the element-wise sigmoid function to each element of the input, resulting in a vector or matrix of the same shape as the input. The sigmoid function is used in neural networks to introduce nonlinearity in the output of a neuron, which allows the network to learn complex patterns in the input data. Derivative of sigmoid function. This code defines the derivative of the sigmoid activation function, which is commonly used in neural networks to compute the gradients during backpropagation. The sigmoid prime function takes a scalar, vector, or matrix Z as input and applies the derivative of the sigmoid function to each element of the input. The derivative of the sigmoid function is defined as exp z/1 plus exp z caret 2. When the input z is a scalar, the sigmoid prime function returns a scalar value representing the derivative of the sigmoid function at the input value. When the input z is a vector or matrix, the sigmoid prime function applies the element-wise derivative of the sigmoid function to each element of the input, resulting in a vector or matrix of the same shape as the input. The derivative of the sigmoid function is used in neural networks to compute the gradients during backpropagation, which is a process that computes the error of the neural network and updates the weights of the network to reduce the error. This code creates a plot that shows the sigmoid function and its derivative over a range of input values. The plot function from the matplotlib library is used to create the plot. The first argument to plot is the x-axis values, which are the input values, test values, for the sigmoid and its derivative. The second argument to plot is the y-axis values, which are the output values of the sigmoid and its derivative for each input value. Two lines are plotted on the same graph. The first line corresponds to the sigmoid function, plotted in blue using the sigmoid function from earlier. The second line corresponds to the derivative of the sigmoid function, plotted in orange using the sigmoid prime function defined in this code. The grid function adds a grid to the plot for improved readability. The legend function adds a legend to the plot, indicating which line corresponds to the sigmoid function and which line corresponds to its derivative. Overall, This code creates a plot that visually shows the sigmoid function and its derivative over a range of input values. The purpose of this plot is to help understand the behavior of the sigmoid function and its derivative, which are commonly used in neural networks for activation and backpropagation, respectively. We can now replace dy_dz3 with f prime of z3. Our final piece of the puzzle is dz3dw2. This term represents the change of z, our third layer activity, with respect to the weights in the second layer. Z3 is the matrix product of our activities, A2, and our weights, W2. The activities from layer 2 are multiplied by their corresponding weights and added together to yield Z3. If we focus on a single synapse for a moment, we see a simple linear relationship between W and Z, whereas the slope. So for each synapse, dz/dw2 is just the activation on that synapse. Another way to think about what the calculus is doing here is that it is backpropagating the error to each weight. By multiplying by the activity on each synapses, the weights that contribute more to the error will have larger activations and yield larger dj/dw2 values, and those weights will be changed more when we perform gradient descent. We need to be careful with our dimensionality here, and if we're clever, we can take care of that summation we got rid of earlier. The first part of our equation, y minus y hat, is of the same dimension as our output data, 3 by 1. F prime of z3 is of the same size, 3 by 1, and our first operation is scalar multiplication. Our resulting 3 by 1 matrix is referred to as the backpropagating error, delta 3. We determined that dz3/dw2 is equal to the activity of each synapse. Each value in delta 3 needs to be multiplied by each activity. We can achieve this by transposing A2 and matrix multiplying by delta 3. What's cool here is that the matrix multiplication also takes care of our earlier omission. It adds up the dj/dw terms across all our examples. Another way to think about what's happening here is that each example our algorithm sees has a certain cost and a certain gradient. The gradient with respect to each example pulls our gradient descent algorithm in a certain direction. It's like every example gets a vote on which way is downhill, and when we perform batch gradient descent we just add together everyone's vote, call it downhill, and move in that direction. We'll code up our gradients in Python in a new method, cost function prime. NumPy's multiply method performs element-wise multiplication, and the dot method performs matrix multiplication. Part of NN class won't work alone, needs to be included in class as shown in below and in part 4.py. Compute derivative with respect to W and W2 for a given X and Y. This code defines the cost function prime method of the neural_network class, which computes the derivative of the cost function with respect to the weights of the neural network. The derivative is used in the backpropagation algorithm to update the weights of the network and reduce the error of the network. The cost function prime method takes the input data x and the target output data y as input. It first calls the forward method to compute the predicted output of the network, y hat, for the given input x. It then computes the derivative of the cost function with respect to the weights by applying the chain rule of calculus. The delta 3 variable represents the error in the output layer of the network, which is the element-wise multiplication of the difference between the target output y and the predicted output y hat, and the derivative of the sigmoid function evaluated at the output of the network. The dj/dw2 variable represents the partial derivative of the cost function with respect to the weights of the output layer. It is computed as the dot product of the transpose of the activation values of the hidden layer, A2, and the error in the output layer, delta 3. Note that this code only computes the derivative of the cost function with respect to the weights of the output layer. The derivative of the cost function with respect to the weights of the hidden layer can be computed using a similar process, which is implemented in the backpropagation method of the neural_network class. We have one final term to compute, dj/dw1. The derivation begins the same way, computing the derivative through our final layer, first dj/dy hat, then dy hat/dz3, and we call these two taken together form our backpropagating error, delta 3. We now take the derivative across our synapses. This is a little different from our job last time, computing the derivative with respect to the weights on our synapses. There's still a nice linear relationship along each synapse, but now we're interested in the rate of change of Z3 with respect to A2. Now the slope is just equal to the weight value for that synapse. We can achieve this mathematically by multiplying by W2 transpose. Our next term to work on is D2/DZ2. This step is just like the derivative across our layer 3 neurons, so we can just multiply by F prime C2. Our final computation here is DZ2/DW1. This is very similar to our DZ3/DW2 computation. There is a simple linear relationship on the synapses between Z2 and W1. In this case though, the slope is the input value, x. We can use the same technique as last time by multiplying by x transpose, effectively applying the derivative, and adding our dj/dw1s together across all our examples. All that's left is to code this equation up in Python. What's cool here is that if we want to make a deeper neural network, we could just stack a bunch of these operations together. Whole class with additions. Define hyperparameters. Weights, parameters. Propagate inputs to network. Apply sigmoid activation function to scalar, vector, or matrix. Gradient of sigmoid. Compute cost for given x, y. Use weights already stored in class. Compute derivative with respect to w and w2 for a given x and y. This is the complete implementation of the neural_network class that defines a simple neural network with one input layer, one hidden layer, and one output layer. The class contains the following methods. __init___ initializes the hyperparameters of the neural network and initializes the weights randomly. Forward propagates the input data through the network and computes the predicted output. Sigmoid computes the sigmoid activation function for scalar, vector, or matrix inputs. Sigmoid prime computes the derivative of the sigmoid function for scalar, vector, or matrix inputs. Cost function computes the cost function for a given input and target output. Cost function prime computes the derivative of the cost function with respect to the weights of the neural network for a given input and target output. The forward method performs a forward pass through the neural network, computing the dot products of the input data and the weights, applying the sigmoid activation function, and propagating the result to the output layer. The sigmoid method applies the sigmoid activation function to scalar, vector, or matrix inputs. The sigmoid prime method computes the derivative of the sigmoid activation function for scalar, vector, or matrix inputs. The cost function method computes the cost function for a given input and target output, which is the mean squared error between the predicted output and the target output. The cost function prime method computes the derivative of the cost function with respect to the weights of the neural network for a given input and target output. It uses the chain rule of calculus to compute the gradients of the cost function with respect to the weights of the output and hidden layers. Overall, this implementation defines a simple neural network and provides methods to compute the forward pass, the cost function, and the gradients for backpropagation. So how should we change our W's to decrease our cost? We can now compute dj/dw, which tells us which way is uphill in our 9-dimensional optimization space. This code creates an instance of the neural_network class and initializes it with random weights. The neural_network class is defined earlier in the code and contains methods for performing a forward pass, computing the cost function, and computing the gradients for backpropagation. By creating an instance of this class, we can use these methods to train and evaluate the neural network on a given task. This code computes the cost function of the neural network for a given input x and target output y. The cost function method of the neural_network class is called with the input x and target output y as arguments. The method computes the predicted output of the neural network for the given input using the forward method, and then computes the mean squared error between the predicted output and the target output. The computed cost is assigned to the variable cost 1. This cost can be used to evaluate the performance of the neural network on the given task, and to track the progress of the network during training. This code computes the gradients of the cost function with respect to the weights of the neural network for a given input x and target output y. The cost function prime method of the neural_network class is called with the input x and target output y as arguments. The method first computes the predicted output of the neural network for the given input using the forward method. The method then computes the derivative of the cost function with respect to the weights of the output layer using the delta3 and djdw2 variables, as explained earlier. It also computes the derivative of the cost function with respect to the weights of the hidden layer using the delta2 and djdw1 variables. The computed gradients are returned as a tuple of two arrays, djdw1 and djdw2. These gradients can be used to update the weights of the neural network using an optimization algorithm such as gradient descent. If we move this way by adding a scalar times our derivative to our weights, our cost will increase, and if we do the opposite, subtract our gradient from our weights, we will move downhill and reduce our cost. This simple step downhill is the core of gradient descent and a key part of how even very sophisticated learning algorithms are trained. This code updates the weights of the neural network using the gradients computed in the previous step. The variable scalar is a hyperparameter that controls the size of the weight updates. It is typically set to a small value such as 0.1 or 0.01. The weights of the neural network are updated using the following equations. nn.w1 equals nn.w1 plus scalar asterisk djdw1. nn.w2 equals nn.w2 plus scalar asterisk djdw2. These equations update the weights of the input to hidden and hidden to output layers, respectively. The updates are proportional to the gradients computed in the previous step, and the size of the updates is controlled by the scalar hyperparameter. After the weights are updated, the code computes the new value of the cost function for the updated weights using the cost function method of the neural_network class. The computed cost is assigned to the variable cost 2. This process of computing the gradients, updating the weights, and computing the cost is typically repeated many times during the training process to minimize the cost and improve the performance of the neural network on the given task. This code prints the values of the cost function before and after the weights of the neural network are updated. The variable cost 1 contains the value of the cost function before the weights are updated, and the variable cost 2 contains the value of the cost function after the weights are updated. By comparing these two values, we can see whether the weight updates improve the performance of the neural network on the given task. The goal of training a neural network is typically to minimize the value of the cost function, so we want to see the cost decreasing over time as the weights are updated. This code Code updates the weights of the neural network in the opposite direction of the gradients computed in the previous step, and then computes the new value of the cost function. The variables dj_dw1 and dj_dw2 contain the gradients of the cost function with respect to the weights of the neural network computed in the previous step. The weights of the neural network are updated using the following equations. nn.w1 equals nn.w1 scalar asterisk dj_dw1. nn.w2 equals nn.w2 scalar asterisk dj_dw2. These equations update the weights of the input to hidden and hidden to output layers, respectively, in the opposite direction of the gradients. The size of the updates is controlled by the scalar hyperparameter. After the weights are updated, the code computes the new value of the cost function for the updated weights using the cost function method of the neural_network class. The computed cost is assigned to the variable cost3. This process of computing the gradients, updating the weights in the opposite direction, and computing the cost is known as backpropagation, and it is the key algorithm used for training neural networks. By repeating this process many times, the neural network gradually learns to make accurate predictions on the given task. This code prints the values of the cost function before and after the weights of the neural network are updated in the opposite direction of the gradients. The variable cost2 contains the value of the cost function after the weights are updated in the direction of the gradients, and the variable cost3 contains the value of the cost function after the weights are updated in the opposite direction of the gradients. By comparing these two values, we can see whether the weight updates improved the performance of the neural network on the given task. If the weight updates were too large or the learning rate was too high, then updating the weights in the opposite direction of the gradients can help to correct the weights and prevent the cost function from increasing. However, if the learning rate is well-tuned, then updating the weights in the opposite direction of the gradients may not be necessary. Next time we'll perform numerical gradient checking check to make sure our math is correct. Part 5. Numerical gradient checking. Last time, we did a bunch of calculus to find the rate of change of our cost, J, with respect to our parameters, W. Although each calculus step was pretty straightforward, it's still easy to make mistakes. What's worse is that our network doesn't have a good way to tell us that it's broken. Code with incorrectly implemented gradients may appear to be functioning just fine. This is the most nefarious kind of error when building complex systems. Big, in-your-face errors suck initially, but it's clear that you must fix this error for your work to succeed. More subtle errors can be more troublesome because they hide in your code and steal hours of your time, slowly degrading performance, while you wonder what the problem is. A good solution here is to test the gradient computation part of our code, just as developer would unit test new portions of their code. We'll combine a simple understanding of the derivative with some mild cleverness to perform numerical gradient checking. If our code passes this test, we can be quite confident that we have computed and coded up our gradients correctly. To get started, let's quickly review derivatives. Derivates tell us the slope, or how steep a function is. Once you're familiar with calculus, it's easy to take for granted the inner workings of the derivative. We just accept that the derivative of x squared is 2x by the power rule. However, depending on how mean your calculus teacher was, you may have spent months not being taught the power rule, and instead required to compute derivatives using the definition. Taking derivatives this way is a bit tedious, but still important. It provides us a deeper understanding of what a derivative is, and it's going to help us solve our current problem. The definition of the derivative is really a glorified slope formula. The numerator gives us the change in y values, while the denominator is a convenient way to express the change in x values. By including the limit, we are applying the slope formula across an infinitely small region. It's like zooming in on our function until it becomes linear. The definition tells us to zoom in until our x distance is infinitely small, but computers can't really handle infinitely small numbers, especially when they're in the bottom parts of fractions. If we try to plug in something too small, we will quickly lose precision. The good news here is that if we plug in something reasonably small, we can still get surprisingly good numerical estimates of the derivative. We'll modify our approach slightly by picking a point in the middle of the interval we would like to test, and call the distance we move in each direction epsilon. Let's test our method with a simple function, x squared. We'll choose a reasonable small value for epsilon, and compute the slope of x squared at a given point by finding the function value just above and just below our test point. We can then compare our result to our symbolic derivative 2x at the test point. If the numbers match, we're in business. This code defines a function called f that takes a scalar or array input x and returns the square of x. The function is defined using the Python syntax def, which defines a new function with the specified name and input arguments. The body of the function consists of a single line of code that returns the value of x squared using the operator. This line of code is indented to indicate that it is part of the function body. The function can be used to evaluate the square of any input value or array. For example, f3 would return 9, and np.array 1, 2, 3 would return the array 1, 4, 9, containing the squares of the input array. This code defines a small positive constant epsilon and assigns the scalar value 1.5 to the variable x. The variable epsilon is assigned the value 1 times 10 to the power of negative 4, which is scientific notation for the decimal value 0.0001. This value is commonly used in numerical calculations as a small value that is close to 0 but not exactly 0, in order to avoid division by 0 or other numerical errors. The variable x is assigned the scalar value 1.5, which is a real number with a decimal point. This value could represent any quantity that is measured as a continuous variable, such as time, distance, or temperature. This code computes an approximation of the derivative of the function f at the point x, using a numerical method called finite difference approximation. The variable numerical gradient is assigned the value of the finite difference approximation of the derivative of f at the point x. The formula for the finite difference approximation is f x plus epsilon f x epsilon / 2 asterisk epsilon. This formula estimates the slope of the tangent line to the graph of f at the point x, using a small value of epsilon to compute the difference between f x plus epsilon and f x epsilon. The numerator of the formula computes the difference between f x plus epsilon and f x epsilon, which approximates the change in f over a small interval around the point x. The denominator of the formula scales this difference by 2 asterisk epsilon, which normalizes the estimate of the slope to the size of the interval around x. The resulting value of numerical gradient is an approximation of the derivative of f at the point x. This approximation can be useful for numerical optimization methods that require the gradient of a function, such as gradient descent. The code numerical gradient, 2 asterisk x prints the values of numerical gradient and 2 asterisk x side by side. The variable numerical gradient contains the finite difference approximation of the derivative of f at the point x, computed using the formula f x plus epsilon f x epsilon / 2 asterisk epsilon. The expression 2 asterisk x computes the exact value of the derivative of f at the point x, since f x equals x asterisk 2 and the derivative of f with respect to x is 2 asterisk x. By printing the values of numerical gradient and 2 asterisk x side by side, we can compare the finite difference approximation with the exact value of the derivative. If the value of numerical gradient is close to the value of 2 asterisk x, then the approximation is accurate. If the value of numerical gradient is significantly different from 2 asterisk x, then the approximation may be inaccurate due to rounding errors or a poorly chosen value of epsilon. Add helper functions to our neural network class. Define hyperparameters. Weights parameters. Propagate inputs to network. Apply sigmoid activation function to scalar, vector, or matrix. Gradient of sigmoid. Compute costs for given x, y. Use weights already stored in class. Compute derivative with respect to w and w2 for a given x and y. Helper functions for interacting with other classes. Get w1 and w2 unrolled into vector. Set w1 and w2 using single parameter vector. This code defines a class neural_network that implements a neural network with one hidden layer. The neural network has the following hyperparameters. Input layer size, the number of nodes in the input layer. Hidden layer size, the number of nodes in the hidden layer. Output layer size, the number of nodes in the output layer. The weights, parameters, of the neural network are stored in two matrices, W1, which contains the weights connecting the input layer to the hidden layer, and W2, which contains the weights connecting the hidden layer to the output layer. The class has the following methods. __init__, self-initializes the hyperparameters and randomly initializes the weights. Forward self, x performs a forward pass of the input x through the neural network and returns the predicted output. Sigmoid self, z applies the sigmoid activation function to a scalar, vector, or matrix z. Sigmoid prime self, z computes the derivative of the sigmoid function with respect to z. Cost function self, x, y computes the cost function for a given input x and output y using the current weights. Cost function prime self, x, y computes the derivative of the cost function with respect to w1 and w2 for a given input x and output y. Getparams self returns the weights w1 and w2 unrolled into a vector. Setparams self, param sets the weights w1 and w2 using a single parameter vector. Compute gradients self, x, y computes the gradient of the cost function with respect to the weights w1 and w2 for a given input x and output y. The class is designed to be used in conjunction with other classes or functions to train the neural network using optimization algorithms such as gradient descent. We can use the same approach to numerically evaluate the gradient of our neural network. It's a little more complicated this time, since we have 9 gradient values, and we're interested in the gradient of our cost function. We'll make things simpler by testing one gradient at a time. We'll perturb each weight adding epsilon to the current value and computing the cost function, subtracting epsilon from the current value and computing the cost function, and then computing the slope between these two values. Set perturbation vector. Compute numerical gradient. Return the value we changed to 0. Return params to original value. The compute numerical gradient function takes in a neural underscore network object n, as well as input data x and the corresponding labels y. The function is used to compute the numerical gradient of the cost function of the neural network with respect to the network parameters. The function starts by getting the initial parameters of the network, params initial, using the getParams method of the neural underscore network class. It then initializes an array numgrad with zeros of the same shape as the params initial array, which will be used to store the numerical gradient values. Next, the function loops over each element in the params initial array and sets the corresponding element in the perturb array to a small value e. This array is used to perturb each parameter in the network, one at a time, to calculate the numerical gradient. For each perturbed parameter, the function first adds perturb to params initial using the setParams method of the neural underscore network class. It then computes the cost function, loss2, for the perturbed parameter. The function then subtracts perturb from params initial to compute the cost function, loss1, for the same parameter, but with the opposite perturbation. The numerical gradient is then calculated as the difference between loss2 and loss1, divided by twice the perturbation value e. Finally, the perturbed parameter is reset to 0 by setting the corresponding element in the perturb array to 0. This process is repeated for all parameters in the network. Once all numerical gradients have been computed, the params initial array is reset to its original value using the setParams method of the neural underscore network class. The function then returns a numgrad array containing the numerical gradient values. We'll repeat this process across all our weights, and when we're done we'll have a numerical gradient vector, with the same number of values as we have weights. It's this vector we would like to compare to our official gradient calculation. We see that our vectors appear very similar, which is a good sign, but we need to quantify just how similar they are. A nice way to do this is to divide the norm of the difference by the norm of the sum of the vectors we would like to compare. Typical results should be on the order of 10⁻⁸, or less if you've computed your gradient correctly. And that's it. We can now check our computations and eliminate gradient errors before they become a problem. Next time we'll train our neural network. Part 6, Training. So far we've built a neural network in Python, computed a cost function to let us know how well our network is performing, computed the gradient of our cost function so we can train our network, and last time we numerically validated our gradient computations. After all that work, it's finally time to train our neural network. Back in part 3, we decided to train our network using gradient descent. While gradient descent is conceptually pretty straightforward, its implementation can actually be quite complex, especially as we increase the size and number of layers in our neural network. If we just march downhill with consistent step sizes, we may get stuck in a local minimum or flat spot, we may move too slowly and never reach our minimum, or we may move too quickly and bounce out of our minimum. And remember, all this must happen in high-dimensional space, making things significantly more complex. Gradient descent is a wonderfully clever method, but provides no guarantees that we will converge to a good solution, that we will converge to a solution in a certain amount of time, or that we will converge to a solution at all. The good and bad news here is that this problem is not unique to neural networks. There's an entire field